So what I will tell you about is the first year of a new experiment which we've been developing for the last decade to play with black holes. Okay, so in astronomy, as you will see, we've had behind us a period of about 50 years where we found increasing amount of evidence that such objects exist in various forms, so-called stellar black holes, and all the way up to the most massive systems of 10 billion solar masses called supermassive black holes. I'll talk about that second species. Now, you know, of course, that all of this started with 100 years ago with Einstein and Schwarzschild and the prediction that there should be objects which are so concentrated that they have an event horizon. And it's these objects which, of course, one would like to do also from a physics point of view. So here, astronomy and physics meet again, and of course, we would like to see whether these objects exist. And indeed, 50 years ago, at the same time, more or less, but independently, several pieces of evidence for such objects became available. Again, I won't mention the stellar variety. They also were discovered at that time through X-ray emission. But the objects which I'll talk about are objects which are much more massive, and they showed up in the first radio surveys of the sky in Cambridge as very bright stars optically. So these quasars were very mysterious objects, and the various theorists, you see some of the famous people working on that, basically developed a model where the energy would be released from accreting gas and stars onto massive black holes as the gas penetrates into the inner region and converting gravitational energy, potential energy into thermal energy and then radiation, and then, of course, disappearing into the black hole and let it grow during that period. So that's the massive black hole paradigm. At the same time, as I said, independently, of course, the Kerr-metric was born, so to speak. Roy Kerr proposed what is now, so to speak, the most likely scenario for space-time around objects of this type. There's a third type of a black hole with charge, which we won't consider in astrophysics because the charge would get, basically eliminated from currents. And so the question then is, if these objects power quasars, what's their role in the universe? Do they exist? And so forth. And in fact, it was a very influential paper by Lyndon Bell and Rees in 1971, which basically said, well, if these quasars are powered by accreting massive black holes, maybe that's just, so to speak, very active stages. And maybe the situation is that you have these objects also in less spectacular form in all galaxies, or at least in many galaxies. And indeed, that is what has emerged, that the so-called active galactic nuclei, the quasars, are just the most extreme variety of, and many galaxies, most galaxies, have massive black holes, or at least local mass concentrations, which we think are massive black holes now, but they are not accreting at very large rates, including our own Milky Way. And so here we go and basically can think about a way to test that paradigm through observations or experimental work by basically looking at the most nearby systems, including our Milky Way, and then using test particles, stars, to measure the motions of these stars and verify or not whether there is a central mass concentration through the kinematic observations. And for us, this has been a story of 3 decades now of hunting down the black hole in the galactic center, and briefly summarize for you the different stages of that. It's the 4 8-meter telescope combination of the European Southern Observatory, ESO, in Chile, There's been a second observatory which also has done work on this, namely the Keck Observatory in Hawaii, and then I'll tell you about the work of the two groups doing this kind of work. But our work is this one, and the last step, which I'll describe here in my talk, is the combination, in fact, of these 4 telescopes now to a single big giant telescope of 130 meters in diameter, which we've just managed to do a year ago, and we are now using, as you will see, to investigate the effects of gravity and around the black hole in the galactic center. Now, when you think about what you need to do is you have to measure very precise positions of stars to, precision of a few hundred micro-arcseconds or better. To do so, you take images. In the galactic center, you cannot do this in the optical because the foreground between us and the galactic center contains dust particles, which attenuates the optical radiation by a factor of 10 to the 12. So you have to go to longer wavelengths or shorter wavelengths, however you like. So that the longer wavelength than in the infrared, for instance, allows you to penetrate the dust and there make images of the star cluster in the center. And to see the motions, you really have to do this much better than you can do on the ground with normal techniques. So one of the challenges here is to overcome the disturbances of the Earth atmosphere. This is done through adaptive optics by measuring the perturbations of the wavefront instantaneously and then correcting for it in an apparatus such that the disturbances are taken away and you get more or less diffraction limited on the ground. Of course, you could also do this in space. The Hubble Space Telescope, of course, in principle can do this, but Hubble is a very small telescope, only 2.5 meters in diameter, and it barely works in the infrared, so that's really not been, unfortunately, not been really all that possible. So you have to do this from the ground with the biggest telescopes you can and measure the positions of stars in the galactic center very accurately in imagery. You can also measure the Doppler motions along the line of sight through spectra, and thereby, over time, you accumulate evidence about the mass distribution. So our first instrument, in fact, was not on the VLT, but on a smaller telescope. But it was the first demonstration that this technique actually would work and led within 5 years or so in the 1990s to the first motions. Thereafter, we set into motion to build a whole series of ever better instruments to exploit the VLT, imagers, integral field spectrometers. Then we went over to so-called laser guide star adaptive optics in order to more precisely map out the disturbances of the Earth atmosphere, and finally interferometry, as you will see. So in the first stage of the experiment, we started in 1991. Our American colleagues, Andrea Guess and collaborators, 5 years later, we basically made these images of the central region of our galaxy, very dense star cluster there, surrounding a compact radio source called Sagittarius, a star which you will meet, which is the spot which is marked by X, so to speak, where the black hole might be. And so patiently over a number of years, both groups discovered that as you go inward, the mean motions of the stars within about a parsec or a few light years increase to the center with a Kepler law. So that's the qualitative and quantitative signature of a central mass concentration, which, as you see, happens here on a scale of a few light years. And so if you convert that into a mass, it comes out to be a few million solar masses located somewhere here in the center. Now, if that were stars, you would see an immensely bright concentration of stellar light here, which obviously you don't have. So it's likely that this is a dark mass, and one form of dark mass would be a black hole. Now, by the end 90s, that was a conclusion which was very well demonstrated by both groups. But of course, you could not necessarily exclude that there might be other configurations non-black hole configurations, like, for instance, clusters of neutron stars or clusters of stellar black holes or other dark configurations. So one had to measure more precisely. And nature, in fact, very graciously gave to us stars which were not supposed to be there, namely stars which were orbiting right here in the center. And that led to a whole series of measurements of the same two groups over the next decade, still more precise, which now wasn't measuring only the velocities and the positions, but actually the orbits of stars. And here's the best one of we have, which we started here in '92, then it moved down. The blue points are from the European group and the red points from the US group, and you see they do agree very well on the first turn, and then all of a sudden it turned around. At that point, the star was about 17 light hours from the black hole. 17 light hours is about 3 times the orbital radius of Neptune. So we are talking about solar system scales, remarkable. So, and at that point, that star moved with about 8,000 kilometers per second. So, you know, it's not relativistic, but it's very, very fast. And so if you take, you know, Newton and v squared r over g, you can calculate the mass. What is the mass from that motion and that distance? Well, it's about 4 million solar masses. So that's the same mass which was measured earlier in the more global measurements. But now we know it's on that scale. And here, hardly anything fits in any more than a massive black hole. Some speculative objects like boson stars maybe, but really we have a very, very good case of a candidate for a massive black hole. Now the star has been coming back out here, so we kept measuring, and the good thing is coming back. And so we're right here, and I'll tell you what happened this year. And next year, on the 17th of May, it'll be here. And that's the point where we hope to measure, around that time, to measure the effects of Einstein's gravity and the deviations from Newton's physics on that particular star. Now, it's not only one star we have. Actually, we are measuring the motions of thousands of stars in the center and have orbits for about 45. It's a rather remarkable system, not only for the issue of the black hole, but also for the inner workings and distribution of a dense star cluster in galactic nuclei, which is relevant not only to our galactic center, but to galaxies in general. And you see how random the motions are, which is somewhat surprising if you think about how they might get there. We think they are sort of shot in there and then get captured, while further out they're actually stars in a more disk-like configuration. For this talk, it's sufficient to just comment that it's just a gift which nature gave to us. A gift of a very precise gravitometer, if you like, because we can use the motions of every one of these stars to measure gravity and map out the gravitational field. Now let me say a few words about the central marked spot, the radio source Sagittarius A stars. And what you see here is on that same scale of a light year or so, a few light months, the radio emissions. So that's both Bremsstrahlung, thermal emission in these extended loops of emission, and then this red dot here is a very bright but extremely compact radio source, Sagittarius A star, which the radio astronomers discovered in the 1970s. With intercontinental interferometry, you can actually measure its size. And that's been done with ever better precision. At 1 millimeter, the size of the object is a mere, in radius, a mere 20 microarcseconds. So that's twice the radius of a 4 million solar mass black hole in terms of its event horizon, twice. So we're really talking about scales where, you know, strong gravity should be very important. Now, surprisingly, we only have so-called visibility curves here in one dimension. You might want to see an image. Well, that's another effort which is happening this year. In fact, with a new set of telescopes, including the ALMA facility, a gigantic millimeter interferometer in the south, which has started this year, to actually make an image which might look like something like this. which is a sort of an arc-like structure due to the effects of special relativity and general relativity of gas surrounding that black hole, which would be here, where the dark parts here are due to the fact of the light also being bent, photon orbit, and the so-called shadow. Now, it's interesting that if the shadow would be measurable in this form and combine that to the measurements which I've shown you on the mass from the stellar orbits, that's, in fact, if it's precise enough, a first-order test of the no-hair theorem, because the radius of that shadow depends little on the angular momentum in the Kerr metric, such that the mass is given, of course, by the stellar measurements. And so if it comes out to be the same on that scale, that would be fantastic. I cannot give you a first result of that in this talk. I can tell you that the data were taken. They're very good data. And the team, which is several hundred radio astronomers, is now working on the analysis of the data of this year. So this is called the Event Horizon Telescope. Which is another way of getting at the information in the center. It's interesting that quasars are very bright in the optical and UV. That's due to a very hot gas in a disk called accretion disk around the black hole. In the galactic center, the spectral energy distribution peaks in the radio and millimeter range and then falls off into the infrared. We see it there. As variable emission, then there's a gap, of course, where we cannot see much, and it comes up again in the X-rays. But there's no indication of what we would call a big blue bump. So that means that there's no accretion disk in the galactic center, and the question is, what is the physics around that black hole? Now, we have learned much about this by a little test experiment, which nature let us look at. Namely a gas cloud, perhaps with a central star, we don't know that, which was falling in the data. We could see that since about 2000. What you see here is the position. 0 is the SgrA star position. And this is the Doppler motion. And what you see here is a Kepler orbit, okay? A very radial, almost ellipticity 0.99 radial orbit. And so this cloud, and it is a cloud because you see it is spread here in velocity, which means it's spread spatially. So it's not a star. So as you go, the time goes on, went to a peak, and then it got disrupted because you see it in 1 year on both sides. There it comes back out, and it currently is right here. So what you see here is nothing else but a little gas cloud, which by its own gravity cannot be kept together in the presence of the black hole. So it's tidally disrupted. It's spaghettified, as we know, and basically at the point in 2014 was about 20 times as long as wide. And at the beginning it was compact, and now it's again coming together is compact. That's remarkable, because the simulations which have been done under various assumptions would have assumed that the gas around the black hole would be dense enough so that it would have a hydrodynamic effect, pressure effect, on the little cloud and destroy it, which apparently didn't happen, at least not to a very extensive degree. Now that gives us a very precise density of the gas around the black hole and tells us, in fact, that surrounding of the black hole is fairly empty of hot gas. All right, now, so that's what we know from all these measurements. We know in the mass distance plane, and the distance, of course, is a parameter which we must measure as well and comes out of these measurements, that the object is about 4.3 million solar masses. The accuracy is, at this point, systematically totally determined by the accuracy of the distance, and is a few percent at this point. The statistical accuracy is better than that. And we know it's really truly an object which would look like a black hole. So if you look at the enclosed mass as a function of distance from the center, then out here on large scales you see the increase due to the stellar influence of stars. And then there's a constant mass, constant inward all the way to the star S2, which is the closest star. And then inside, on scale of a few Schwarzschild radii of the mass, you see its size. So that looks like a black hole, smells like a black hole, and probably is a black hole. But of course, to the extent at the present, we can only say this is true if GR is right. So of course, now you would like to turn this around and say, well, if this is indeed a massive black hole, as described by Kermetric, let's use it and test that. But for that, you have to come closer and measure much more precisely than what we've done so far, preferably to this scale. So how would you do this? One way is the event horizon way, basically using light, which is passing through this region, and see how it's bent. The other way is to basically see how the motions of stars here, S2 itself, and inside are influenced by GR effects. And so to make that kind of measurement, we need to have a bigger telescope. And you can realize this, we know this from radio astronomy, through interferometry. Interferometry is basically a way to interfere the light from different telescopes, bring it together, and use the interference of light to get fringes. So basically, here's a two-element interferometer. The waves come in from some direction from a distant star, and then by compensating for this path length delta here, you can then add the light, which comes here and here, to form fringes. Now, obviously, what you need to do before you can add the light, you have to, subtract this path length difference, this geometric path length difference. In the VLT, this is done underground in a tunnel system where you have little carriages which basically, move with the motion of the star and the telescope in order to compensate for this effect. So to first order, then, you can combine the light. Now, first order is not good enough. See, radio astronomers have done this kind of interferometry for 50 years, but there you're dealing with wavelengths which are 10 to the 4 times longer than in the infrared. Plus you have typically, at least initially, very narrow bandwidth, so that your fringe, so to speak, your coherence patch, is very wide, centimeter wide. Our coherence patch in the infrared or optical with very broad bandwidth of the detectors is less than a nanometer. So we have to actually measure everything to about 5 nanometers, correct everything to a few nanometers, send lasers through the system, and make sure that we somehow are able to be on that fringe. Now, in order to do that, we cannot rely basically on a stable measurement, because the Earth atmosphere moves around with a kilohertz frequency. So in the end, we decided to do this through a differential experiment by basically looking at a star and the galactic center, which are about 1 arcsecond apart, use the star to find the fringes, and then basically correct the entire instrument so that we can sit on the fringe, and then we can measure the galactic center. Now, this experiment was designed about, as I said, a decade ago by a group headed by Frank Eisenhower at our institute, who is the PI, a very strong contingent in France, some German institutes, and ESO itself, plus a group in Portugal. And this is a very difficult experiment. We've done many experiments in astronomy. This one is the most difficult we've ever worked on, I have to tell you. And to impress you, what I've done is made a little movie which shows you the fate of the poor photon, which happens to go from the galactic center into the central region. And there you see how complicated an instrument this might be. So here we go. Photon comes in, goes into the Atacama Desert. There's one telescope. So it bounces now from the usual wave in order to be brought from the main tertiary mirror down to the coude, because we need to bring the light together. And there's many bounces in order to get to the bottom of the telescope. The next thing we need to do, we need to phase the telescope. And so down there in the Coude, we have a bench here where we now measure and correct for the distortion of the Earth atmosphere. Now comes the light from the 4 telescopes together. I described to you already that here we are correcting for the geometric path lengths, and now we're bringing the light together in a device which is a Doer cryogenic system where the 4 inputs now from the 4 telescopes come in. Now we have to prepare the light. We have to basically position it. We also have to pick the light from the 2 positions on the sky, the star, and the galactic center for all the 4 telescopes. We also have to derotate the sky. We have to make sure that we are coherent, so there's a whole pre-optic system here where we do all of this machinery. Now then, in order to make this very compact, we now go from free space optics into monomode fibers. So then we can basically make the system much more compact than has been possible in cryogenic environments. So we now go from the free optics, in a second you'll see, into the fibers. 2 fibers per telescope for the star and the galactic center. We can, through these fiber bundles, which we have in here, actually make a control of the path length difference, which is due to the Earth atmosphere. Once we measure the fringes, we also can control the polarization of the system. So we have many fibers going through there. And now we have to combine the light in order to make the interference. Now that is also done in a very sophisticated new way, namely integrated optics, not just big beam combinations, but integrated optics. Down there you see this little chip of a few centimeters in size, where you come in with 4 input beams and 24 output beams with all the different delay lines, so they can do interferometry. Then we go through a spectrometer. And finally, we combine all of this onto a single detector, which we had to develop, which has essentially no noise at the kilohertz readout noise. That was required in order to be able to actually see the Tuck star, which is a fairly faint star, 10th magnitude star, in the coherence time of the Earth atmosphere, which is a millisecond. So you need to do that in order to be sure you can actually track. So you see, it's not a simple instrument, and it took us a few years to build that, and I'm very, very delighted to say that it came together very nicely. And here's the first image of the galactic center region. So we put a fiber, so remember, we are tracking the fringes here on a star which is an arcsecond away. We stop the fringes, and now we can integrate away much longer than the coherence time of the atmosphere and do a Fourier inversion, which is what you need to do with 4 telescopes. And now you can see the 2 objects here. S2 is the star which is coming in right now for its next peri, and 65 milliarc seconds away from it is the galactic center. There is the black hole, SgrA star. Now you see all of these other smudges here. That's due to the poor beam combination of 4 telescopes. 4 telescopes instantaneously, they do not make a very good image. Okay, that's very well known. And so this is the degree to which we can currently see. We can see this double source. Resolution is about 2 by 5 milliarc seconds. So that's on the small axis, about 30 times better than a single big telescope. So that's what we wanted to achieve. We also can measure the position of these sources currently to better than 100 microarc seconds, about 50 to 100 microarc seconds. We still would like to do better, but that's what was achieved in the first year. So here we are. Now, the first thing we are really proud of is that this instrument is able to see objects here down to magnitude K of 19. K is the logarithmic the indication of flux in the 2-micron band, 19. So for you as physicists, I should say, this is about a factor of 600 to 800 fainter than anything which has been done in this field. Because anything done in the field so far relied on detection within the coherence patch of the atmosphere, while here, of course, you're beating this in various ways. So it's a very faint, very high sensitivity apparatus, which, by the way, cannot only be used for the galactic center, of course. There are many, many other applications, X-ray binaries, exoplanets, star-forming regions, etc. But, of course, we are mainly interested now in this thing. Now, there are some things we haven't done yet. We have not yet understood fully the shape, the form of all these side lobes here. In radio astronomy, that's understood to be just the inverse, the Fourier inverse of the so-called UV coverage. That's not quite the case here, and we are working on being able to remove these in order to then see perhaps fainter sources and perhaps stars which might still be closer to the central black hole. But that can be done anytime. We're working on it right now. Right now, we are focusing now on measuring the orbit of this object as it's coming in. Now, the galactic center black hole itself, we knew was variable. So from earlier observations, if you look as a function of flux, the probability to see the source is very rarely bright and very frequently faint. That's what we knew. It's always variable. Now with gravity, we've pushed that another magnitude down to basically show that this distribution is more or less log normal. So over the last year, this year, you can see how it's been varying. So that's good. We see the black hole all the time, but it's not so good because a variable source to image around a variable source is very shall we say, bitchy. That we know that from interferometry because the Fourier transform technique uses normally stationary emission, so we have to work around that. Now this is synchrotron emission of very hot electrons of a relativistic gamma of 1,000, which are excited by probably magnetic effects in the inner corona around the black hole. So that would be very interesting to see move also. And so we'll work on that. So now let's concentrate on what we have achieved this year in terms of the orbit. So here's the diffraction-limited imagery from the black hole of the central star cluster. The black hole is that yellow cross. The star S2, whose orbit I've shown you before, is here. There's the star. But you see there are many other stars. So one of the limitations of current work with the single telescopes is this crowding with all the other stars. So by interferometry, of course, we are overcoming this. So here's the orbit of S2. And so then if you look at this with interferometry, then you see what I've already shown you, namely a very clean image at this point. So the star currently is 500 astronomical units. 6,000 Schwarzschild radii, and it's coming in. So in this year alone, we have done a number of measurements. So when the star came around 15 years for the first time, that was our accuracy of the measurements. That was the astrometric performance during the first peri in 2001-2. This year, we are making measurements in these green circles with adaptive optics work on single telescopes also. That's our standard way with NACO, and that has an accuracy of about 400 micro arc seconds. That's the measurement here, so you see the orbit as the star moves in. Now with the interferometer, we measure much more precisely. Now you see the red dots. These are the measurements in the different months in this year. So better than 100 micro arc seconds. Still not good enough, perhaps, as we had hoped, but we'll improve on that. We are seeing the motion now from night to night, 140 micro arc seconds per night, and it's going to accelerate now over the next month. Right now, we have a break. It's not a strike. It's the it's the sun which is unfortunately in front of the Galactic Center. So we all have finally a break. I can tell you that team doing this work has been down in Chile every 3 weeks. Bang, bang, bang. Tremendously hard work. So it'll start again in February, and we are all eagerly looking forward, of course, to that epoch. So what will we see next year? Well, the first term in the post-Newtonian corrections of our orbit is the gravitational redshift and the Doppler effect. And here are the residual Doppler motions of the star S2 relative to the best fitting Newtonian orbit, which is a 0. And the GR effect is predicted to be this. And you see, it's flat here so far, and it's beginning to pick up. So if this continues, we are fairly confident that by summer next year, which is here, we'll have a first detection, very significant one. And I would assume that our colleagues at UCLA will also be able to do the same, because this is not astrometry, this is just spectroscopy. The astrometry is more difficult. Here, let's just plot in one coordinate the deviation from the residuals from a Kepler orbit. Again, the dotted is the best fitting Kepler orbit, and that's the GR orbit here. So in the galactic center, that star S2 basically makes a little kink as it comes in. And the Schwarzschild term is 12 arc minutes. So that's what we need to measure, a 12 arc minute deviation from the best fitting Kepler orbit. You see, with single telescope astrometry, that's hopeless. You cannot do that. But already this year, we put basically good enough measurements down that by measuring 2 more years, we hope to have a 5-6 sigma detection of the Schwarzschild term. So that's basically a step or two of a ladder of ever more complex tests of GR. So we are very confident this will come next year. The prograde precession, I would say, if we continue working the way we have, very likely to come in about 2 years. How about the spin of the black hole? That would be the frame dragging and the quadrupole effect in lens steering. Well, that we cannot do on the star S2. That's very clear. For that, you need to have a star which is further in than S2 by about a factor of 5 in radius. We have not seen such a star yet, but that's why the imaging, which I described to you, is so important. It would move very fast and would have orbital timescales of a few years. So it would be tremendously exciting if such a star would be there. And again, we are hoping that nature will help us again. Now, the next step is basically the shadow, which I explained to you, for which the experiment has begun. The millimeter team has taken the first data set and are analyzing it. And I mentioned to you that if we have a shadow size, since we know the mass and the distance, we have a first order test of no hair. Beyond this, we'll have to see. Obviously, you have to really be very, very, very close to the black hole. Potentially, the infrared emission, the synchrotron emission, might do that for you on a scale of a few times the event horizon size, but that's speculation. Now, of course, gravitational waves are still better in a way. Now, the next time in the galactic center, very likely you will see emission of gravitational waves in about 10 to 20,000 years, which is when the next likely, statistically, star disruption will happen. So for that, you will have to be patient. Of course, in the meantime, when LISA comes, which we hope to be in about 20 years from now or so, space experiment to measure the gravitational waves, well, then we might be able to see these kinds of effects around massive black holes also at larger distances. So in summary, then, we are actually in a very unusual time. 100 years after Einstein, a number of avenues of difficult experiments, the gravitational waves, currently ground-based with LIGO, and Virgo, and in the future LISA, and then here these experiments on the Galactic Center with stellar motions and light are for the first time really probing these exciting objects called massive black holes. And here are greetings from our team, and thank you for having me.
Thank you very much for describing these beautiful measurements.